Yeah, I wouldn't say it would start being significant until about right here. Okay, even with 50% vaccinated, you still have a lot of disease there. So why is this? Because, well, if you're not vaccinated, then you're passing things on, right? Okay, but the more people that are vaccinated, they may still get the infection, but they're asymptomatic or they're not producing a lot of high viral titer. And so the chance of transmission is much lower. So this is why we like to see high vaccination rates in a population. So influenza, this is actually why we're having a problem. Anybody know what the current vaccination rate is for the state of California? The whole state. They didn't. You want to guess? 40 to 50%. Okay. So where are we here? We're over here, right? We're over here, so we're still going to see a lot of infection. And you couple that with, maybe it's not as good a match as it should be, we're getting trouble. And that's what's going on right now. So anyway, so a little something that's in the news. It's kind of interesting. Okay, let me see who's here. It's 9:30. If you have your student information sheets, please pass them up so they make it up here. Okay, Ariana. Good. Terrence. Terrence here? Andrew.
Hi.
How are you?
I'm doing well, yourself?
Good, I can't complain. You're great.
Thank you.
Happy and healthy? Right on, okay. Oh, that's so cool. Oh, good. Rossi? Who's Rossi? There's Rossi. Okay. Julian. Good. Vivian. There's Vivian. Good. Okay. Tyler. Good. Michaela. Where? Where? Oh, good. Gotcha. Nancy. Good. Talia. Good. Arthur. No, Arthur. Jenna. Brenda. Good. Finally. I'm glad you made it. Tamiko. Right on, right on. Oh boy, where's my notes for pronunciation here? I don't see it. Okay. I'm mistaken again. Okay, one more. How do you say it again? Zaldi. Okay. Savali. Okay. Call you what? Yuri? Okay. Gotcha. Anna. It's here. Good. Josh. Excellent. Joanna. Good. Manuel. Annabelle. Okay. Maritza. Where? Oh. Melissa. Alexandra? Good. Okay, Melissa Torres. Where's Melissa Torres? Grace? All right. And Julissa. Okay. All right. Haley? Haley Akey? Okay. Victoria. Okay, Victoria. Sydney. Okay. Ebony. Where's Ebony? Oh, there we go. Excellent. Madeline. Good. Chloe. Oh, good. Michelle. Michelle Day. There. Okay. Sierra Ferguson. Right on. Keith. Okay. Alia? Okay, gotcha. Catherine Herrera. Right on. Jada. Jesse. Victor. Good. I owe you an email. I haven't forgotten. Soleil. Okay. Alyssa Martinez. Good. Anaya. Good. Justice. Raul. James. Good. Ivan is here. Okay. Paulette. Anna. No Anna?
What's the last name?
Anna Yepes. Oh, there you go. Okay. Mina Hall. Good. All right. For this section 43132, who's your lab instructor?
Eric?
Herrick. Okay. You gotta keep him in line, don't you? Okay. Fabian. Right on. Veronica. Good. Eliana Crespo. Good. You made it. Good. Okay. Eliza. Yeah. Emily Escoto. Okay. Leonard Garcia. Right on. 68 whiskey. Right on. Good. Still in reserve? No, you done? All that good stuff? I love my 68 whiskeys. They can do anything. Right on. Okay, Janet. Yeah. Kimberly. Jimena Fernandez. No go. Rafael. Good. Tatiana Lopez. Good. Caitlin Morales. All right. Gabriella. Eric.
Here.
Good. Samantha Orr. Jetta Perez.
Here.
Jacob.
Here.
Yeah, good. I think I have a solution. Yeah, yeah. Titsali. Okay. Desiree. Mustafa. Here. Kate. Santana. Maritza. Vera. Okay. Kiana Williams. And Janet. Where's Janet? Good. And you all have Friday lab, correct? And you've got Heidi Ramirez, right? Okay. Did she do a good job? Yeah. Okay. Cool. All right. So, I was looking over your work for this week, all the quizzes and things like that. You did pretty well, I gotta say. Pretty good. We're gonna have another review quiz this week on Chapter 5 Metabolism. Again, it will open on Wednesday. You have until Sunday to do it. You have 2 attempts, excuse me. So I will put is that moving or is that just I'm drunk? Okay, that's moving. Okay. I'm not sure. Like, whoa, okay. All right. So that's really bad. That's not good. Okay. Okay. So anyway, I'll put a review sheet up for metabolism. For metabolism, what are those things? Glycolysis. All right, aerobic respiration, anaerobic respiration, fermentation, all of that good stuff. Remember all the inputs and outputs and things like that, where it happens. So that's what this quiz will be about. Enzymes, okay, things, again, that you learned in other classes. So, okay, so that's good. All right, let me talk about a couple of other things here. Okay. Yeah, this is this week here. Okay, how to prepare disease cards in this class. Do you want the lights down a little bit so you can see better? Okay. All right, so this week is your preparation for disease cards, and you're gonna do it in groups of 2 or 3. Okay, no Lone Rangers here because I want to know who's in your group. In fact, why don't you establish your group right now? Get your group, and I want a piece of paper with your 3 names and your lab days on them, okay? So I'll give you a minute to find out who your groups are. Yeah? No, so I want a list of your names and your lab days so I know that you're working together as a group. Okay? Okay, when you've got your list, bring it on up. So we have it up here, I can have it. You got your name and your lab day. Don't have your lab day there. Okay. Yeah, FAM, yeah.
I just want to double check.
Spray PM works? Okay. Good morning. It is a good morning, isn't it? We're all here. No, don't. Because, oh, you know what? These might be 10 years old. Oh, seriously, wow. With a water bottle. Yeah. What do you need? Let me see. And here you go. Are you up to date on your tetanus? No. If you don't know, then get a tetanus shot. Yeah, wash it off and then do it. No? Okay. No. Okay. Coolie. Okay, I got everybody's? No. Last call. Come on, come on. Microscopic papers for micro. Okay. All right. You got your peeps, right? So this is who you're going to work with this week to get these cards done. All right? Not the little cards. You want the bigger cards. Okay? The bigger cards to do this. Okay? And you'll say, oh, can I just print it out? No, it's got to be on a card. Part of this class, remember, is following directions. Okay? And there is method to my madness. So please make sure to follow. Okay? Group of 3 students, 2 is okay, 4 is not. You cannot be a group of 1. Okay? Do divide the labor. Okay? So you're going to be making your cards with your information that's in your textbook only. Okay? Why? Because you can go down a rabbit hole. There's medical microbiology taught in a medical school, and it's going to have a lot more detail than we have. So stick with the textbook and that Talaro Appendix D, okay? All right? Give everyone in the group a copy of the cards. You make well of advance. Everyone needs a complete set of cards. How many are we going to be doing this week? 10, okay? 10. So do Appendix D, all right? Use the Talaro textbook, great introduction. 1 disease paragraph per disease, okay? So you're gonna get 1 per disease, okay? Wow, that's really just not good. Okay. Color in words, highlighters, okay? So to get you started on this, All right, we've got the first 10 diseases right here. Okay, we're doing gram-positive cocci and staph and streps. So if you go through this, you've already got the diseases here. And do you need to know these terms? Yes, you do. Okay, all right. You can use your cards on Wednesday's Quizzy Wizzy, because we have a quiz on Wednesday, right? Yeah, so you're going to be busy doing cards for the first, and you can use the cards on the first Quizzy Wizzy. Okay, and so all the information that you need on your cards is here. So just print these out and do the cards. So most of the work is already done for you. Okay, now I know doing these the first time you're gonna be like, oh, I'm not sure. Okay, that's okay. You'll probably end up redoing them, maybe redoing them again as we go through chapter 13. Okay, but this is a work in progress. You're going to know these infections very well. Okay, any questions on the disease cards? Yes. Everybody needs their own set of 10. You're going to divide the work up this week to get the 10 done, but you all need the card, the set of 10, because you can't be looking at theirs for your quiz, right? You've got to have your own. Okay. Yes.
Can it do minuses front and back or just front?
Think about when you're studying. You could do front and back and see if that works for you. Because multiple cards usually don't. That's too much time, you know, and it's not consolidated enough. So try it just, you know, try it just one. See how it works. Okay? Yeah.
So all the information for this week's 10
Yeah, to help you out. So you got to go through and make sure. So what things should you be really paying attention to? I've got what we call in micro mama sheets. Okay. Mama sheets are kind of like, you've got all your cards and then you've got this to kind of reference, okay? You're gonna do mama sheets in lab, we're gonna do mama sheets for the final, okay? It's just kind of the big sheet that has everything. But yeah, so look at the ideological agent. Remember, we talked about writing this last time. This has gotta be capital, this is small case, okay? And then the system. That's what we wanna focus on, okay? You're not gonna, you know, so for example, if you've got, one of the things to pay attention to on the cards is a system. You might wanna highlight all the systems one color, okay? You might wanna highlight toxins all one color, you know, that kind of thing, okay? So think about how to study. So you've got a tremendous head start this week, which is good because our Quizzy Wizzy is Wednesday. It's unfortunate we didn't start Monday, but you know, it's going to be busy. But you can do this, okay? You've got it. Any other questions on disease cards for Wednesday? Yes.
You know what the size of the disease cards are?
It's the bigger cards. I don't know off the top of my head what it is.
5x8?
5x8, yeah. Make the bigger one so you can actually see them. Yeah. Yeah, part of the quiz is going to be on the disease card, so you want them ready to go. Yep. Okay, yes?
Off topic, but are these all going to be on the final, like in terms of are we going to be able to use those cards, or are we going
No. By the time you get to the final, no cards. You're just going to go in with your brain because it's all there. Yeah, So, yeah, all there. Okay, cool. Any other questions about disease cards? This is a process, I understand, but we'll do this first round. Yeah?
So just to clarify, the systems that you have like 1 through 10, because I saw some of them were like 1 through 5, we put those on a individual card or?
Right, everything will be on an individual card. So let's go back here for a second. Okay. Unit, disease, names, and systems. So yeah. Wait a minute, that's not what I wanted. What I wanted was this one. Okay. Okay, so on your list of diseases, you have disease 1 through 5, right? And diseases 1 through 5 all are the causative agents is Staphylococcus aureus, right? Okay, so then what do you want to do? You want to make sure all of this information is on those cards, each one of it. So for each disease, you've got, you know, because Staph aureus causes a ton of different diseases. So that's why one card. So you should have a total of 10 cards. Does that make sense? Okay, cool. All right, good. I know it's painful doing something new, but we'll get through it. Okay, but yeah, you've got you know, number of questions for each. 2, 3, 4, 5, 6, 7, 8, 9. Yep. What's the name? Okay. All right, good. Also on here, put a nudge sheet so you can start preparing for midterm 1. Okay, and off we go. So, cool. Any other questions? All right, let's get going with today. Did we do this last time? Help me remember. Wednesday was a long time ago. And we did this, and we did this, and we looked at diseases of the poor, correct? And epidemics, and vaccination versus non-vaccination. We saw these, right?
Yep.
Okay, and we got to this one, and I think we left off. Did we do this one? Okay, what about this one? Oh, good. We left off here, right? Okay, now I'm starting to remember. Yeah. Okay. So, again, a lot of this is from you've had in your pre-req classes, like Bio 1 or 50A or 50B or all of those. Why is this weird? Let's try this. There we go. Okay, so the steps in the scientific method. Observation, asking a question. What makes a good scientific question?
If you can test it.
If you test it and, all right, it's actually answerable, right? Yeah, it have to be answerable. Okay, then you come up with a hypothesis. What's a good definition of a hypothesis? Remember this? An educated guess? That's good. What does it mean? Okay, what you think will happen, it's based on things, okay? Try and link this back to the question, that this is a probable answer to your question, okay? And then make a prediction and perform experiments. Great. What are the things we have to think about when we do an experiment? Yeah.
Someone else has to be able to repeat it, get similar results.
Okay, it's got to be repeatable. Okay, good. Yeah. What about the control group? What's the other group?
Experimental.
Experimental. What's the difference between the control group and the experimental group? Okay, a little more detail. What's happening? What do you do? Yes.
The control group stays constant and the experimental group is changing on the variables.
Okay, good. Yeah. And which group is compared to each other?
We usually keep the control group as a baseline.
Right. Good. Okay. What are constant variables in an experiment?
Temperature.
Oh, it depends on what the experiment is, right? Yeah. But it's a constant variable does exactly what its name says. You want to put your phone away, please? Oh, gotcha. Oh, bring it up here so you can actually hear it. Okay. Are you recording too? Does that give you permission to? Okay. Do you want to bring it up? Yeah, bring it up, Rose, because you're going to get ventilation noise. No, if you are, you're going to bring it up there. Okay. So, okay, can you turn it? Okay, so what a constant variable stays constant during the whole experiment, right? So for example, if we were looking at an experiment that was looking at reducing blood pressure, what are some of the constant variables we would want? Yes?
Someone drinking like the same amount of water.
Okay, so same level of hydration. What else? Yeah.
Age group.
Age group, good. Yes. Activity level, yeah. So those are the things you want to stay constant. Let me tell you, in the perfect experiment, it has one variable. Is that really possible when you're doing human research? No. So what do you have to make up for it in order to get all of everybody accounted for? What do you do? Sample size. Very good. So what is the rule about sample size? The bigger the better, right? The bigger the better. You look at big pharmaceutical studies, they have between 10,000 and 100,000 folks in it if it's going to be good. Okay? Costs them a lot of money. Oh, it's too bad, so sad, right? Because you want to be able to collect any information about that drug. Okay? So, yeah. Okay. So, independent and dependent variables. What is a dependent variable?
Something that changes
Okay,
as a result.
it changes as a result and it's measured, right? It's whatever gets measured. If you're measuring, if it's a drug that's looking at blood pressure, what's your dependent variable? Blood pressure. That's what you're measuring, okay? What's an independent variable? Come on, this is review. What is an independent variable? What the experimenter changed. Good. What's a double-blind study? Okay, good. So the person getting experimented on and the experimenter don't know what if they're giving the placebo or the actual drug. It's managed by a third party. Okay. If you become an RN and you decide, man, I really don't like being on the floors, I don't like people throwing up on me, one of the jobs that you can do is there are companies that manage experimental studies, and they hire RNs to ensure that the process is being done correctly. Okay, it's pretty lucrative. My friends that do it get about 250 grand. You got a lot of responsibility though. You want more money, it's more responsibility, right? If they screw up, I mean, do you know how much it costs to get a drug from the lab to market? So it's actually prescribed? You're running about $18 billion. 18 billion, okay? 90% of the drugs that start off in the lab never make it to the market, okay? There's too much toxicity, there's this, there's that, there's, we get this adverse effect, or it's not as effective in the clinic as we thought it would be, okay? If the nurses screw up on the experimental supervision, you're talking a lot of money for that business. Do you see why they get paid so much? Tons of responsibility. They got to do it exactly right. So, okay, now what do? You analyze the data. Then what do you do with your data once you analyze it and develop a conclusion? Where does it go? Come on, this is review.
Peer review.
Okay, go back up. Does your data support your hypothesis or not? Okay. If it does, what do you do with the hypothesis? If your data supports it, what do? Keep it. Okay. If the data does not support the hypothesis, what do? Okay, start over. Okay, and if it does support the hypothesis, then you can communicate and publish it. Okay, you got to know these things. Why? Because you're going to be doing this all semester long. What is your last project in the micro lab? Unknown. If you can't go through this and you don't know all the parts of it, you're going to be lost. Okay, so hopefully you have written everything down that has to do with, how to do scientific method. Okay. Any questions about scientific method? Good? Okay, excellent. All right. Okay, go ahead. You should have your PowerPoints with you or printed out or something. Okay, take a moment, fill them in. What belongs here? Okay, go ahead and fill them in right now. got these slides filled in? Okay, you're in the wrong PowerPoint presentation. Okay, so what comes first? Hypothesis. Then what do? Design an experiment. And then you collect data, and then
Reject or accept hypothesis.
what is it?
Reject.
Reject or accept the hypothesis, retest, and what does it come out to be? The theory, if you have enough of the positive and it works and it works and it works a million times over, then what do we develop?
A law.
A law. Good. Okay, any questions on that? Okay. All right, let's talk about PowerPoints here. I put a lot of blanks in PowerPoints. What I would recommend that you do before you come to class is you fill them all out. Okay, chapter 13 is posted. We're going to start chapter 13 and finish it up on Wednesday. Okay, but you should print them out. Okay, if you're trying to type things in, it's going to be too slow. I'll tell you that right now. Okay, some of you don't even, are trying to do everything on an iPad. That's great if it works for you, but don't be hindered by it. Okay, always carry a notebook with you, even though if you have everything electronically, because what happens if internet goes out? You're in trouble, right? You're in trouble. Has that happened before? Yeah. Have we lost power? Yes. Okay, so always come with a backup, plan A, plan B, right? Okay, so how many have printed out chapter 13 ones yet? Good for you, good, good. All right, I hope everybody has chapter 13, and when you get it filled in before you come in. So that way, not only you're hearing it for the second time, maybe the third time, okay? Does that make sense? Okay, cool. All right, let's look at this. All right, we're going to start talking about some of the important experiments in microbiology, because it's only been in the last couple hundred years that we've understood what the heck is going on with microbes, and even then we're still learning all the time. Okay, what belongs in these blanks up here?
Biogenesis.
Biogenesis versus
Spontaneous generation.
spontaneous generation. Okay, Aristotle. You've heard of Aristotle, right?
Mm-hmm.
Okay, ancient Greek philosopher. Okay, he said that had this belief that non-living matter, living things could come from non-living things, and why? Because he looked at plants and would see, meat. He looked at plants that would have insects on them. But plants living too. I never understood that observation, but maybe he was drunk too. I don't know. So, but yeah, you see it. If you left out bread, it became, there were living things that would grow out of it. And so he said, it is readily observable that aphids arise from the dew which falls on plants, and fleas from putrid matter, and mice from dirty hay. Okay, pretty good for back then. 350 BC or so. Okay, this belief remained unchallenged for how long? 2,000 years. 2,000 years, that's a long time. Okay, until here come the rebels. All right, we started looking at cells. All right, now one of the first theories that you learned back in Bio 1 is cell theory. What does cell theory say? All living things are made of cells, and all cells come from other cells. Those are the two ideas about cell theory. Okay, well, guess what happened? 1616, Robert Hooke developed a microscope, and he looked at dead cells. What did he look at? He looked at cork. Where do we see cork these days? Wine corks, right? Now, some of the wine corks are synthetic, but you get a good wine, it's usually got a cork on there. And he would take very, very small shavings of it and look at it under these lenses under his microscope. And what he said were like little rooms that the monks would stay in. And they would call those cells. And so that's what he called, that's where the term cell came from, is from this cork that he saw in the 1600s. Okay? Now, here comes Antoine van Leeuwenhoek, okay? And this is his microscope. It was so small. He brought it to parties. Can you imagine what would happen if we brought a microscope to a party? That's the last invitation we'd get, right? But back then, think about back then, open sewers. Okay? Open sewers. You had one central well for the water that everybody used, and they didn't wash their hands. They didn't need to. They didn't even know about they needed to wash their hands. Do you have a question? Good? Okay. So, what did Van Leeuwenhoek do? He was the first to look at living things, and what he would do is go to the sewers and get little samples and put it in his little microscope and take them to parties, and he saw little living things swimming around in there. And it was really cool, okay? So that was the first microscope. You're gonna see swimmers in any open water? Absolutely. Any water that's left open, you're gonna see swimmers. Okay, and it's not necessarily just bacteria. What else is gonna be in contaminated water? What?
Microbes,
Such as?
bacteria.
Okay, besides bacteria, what else is in microbes? Anybody go camping around here? Okay, what's in the water? In every water system in our mountains? Giardia. What is Giardia? It's a little protozoan, okay? And if you've ever had Giardia, you have the most aromatic gas ever known on this planet. Oh my gosh, it is so bad. Have you ever had a Giardia patient? Oh, you're gonna have fun. Okay, not only do you have terrible diarrhea and that, but the gas, oh my gosh. Ugh. So, all right, we'll come back to the little animals that Van Leeuwenhoek saw. So Francesco, what's his last name? Redi, okay. He is in the 1600s, so a lot of things started changing in the 1600s, okay? And he was the first scientist that actually asked the question, does life arise from non-living matter? And he designed a good experiment that disproves spontaneous generation. He proposed this idea of biogenesis, that life has to come from pre-existing life, okay? And it had to do with meat and maggots, okay? Does meat spontaneously make maggots? No. If it does, what do you know about that meat? It's contaminated. Don't eat it. Gross, okay? Look at the hair. I love that hair. Yeah, this is cool. Okay, so here's the experiment. So he took a jar, put some raw meat in there, old meat, flies could come in. He had a jar that had meat and it had a screen that would let some things in and not others. And then one that was completely sealed off. Tell me which ones could grow something. First two, okay? What's the key here? You left it open, okay? These little holes will let other things in. It might not let those big flies, but it will let other things in, okay? So this was his rotting meat experiment, okay? And he was able to show, hey, if you seal it off, you don't grow maggots. Ta-da! Okay, so here's Anthony van Leeuwenhoek, who we just talked about, okay? And he used a microscope, saw a different magnification. 270 times, that's his little microscope. That works pretty good. What's your limit on the microscopes in lab? 1000x. Okay, what's the medium range magnification on your microscope? Low power lens. Low power is what? 40?
Yeah.
4 is scanning. 10 is, do you have a 10, right? 10, that's usually your low power. Okay, 40 is, yeah, a little bit higher, and then your 100x, and you do oil immersion. You're gonna do oil immersion this week, right? I don't think you did it last week.
We did last.
Oh, you did? Okay, all right, except Monday's lab didn't.
No.
So you haven't had lab yet,
All right.
so you get to do it this week, so, yeah, okay, good. All right. So, let's talk about more of the spontaneous generation debate. So, can you list right now all the scientists that we've talked about so far?
Loonhope, Reddy.
Okay, and what they've done, okay? Do you think this is gonna be on the exam? Yes, I always have a section of famous scientists, okay. All right, so here's Needham, okay, and what this did, and we're 100 years ahead now, okay, oh, maybe between 50 and 100, okay, and took chicken broth. Chicken broth, what does chicken broth have in it? Lots of proteins and carbohydrates and lipids and things like that, and so it should grow anything, okay? And heat it up, heat the flask up, looks clean, leave it exposed to air, what happens? Get microbes in it. Okay, what happens when you seal it? I know this is kind of a misnomer because you can't really boil this stuff and then this will blow up. But yeah, keep it closed, what happened? No microbes. That's a great experiment. Doesn't really show it conclusively, but it did say, hey, any microbes that are going to be growing come from the air. Okay? So, Spallanzani just repeated them and came up with a nice conclusion. But it still isn't done. Here we are. This is it. Which scientist is this?
Pasture.
Pasteur. He did the definitive experiment, okay? And he used what these are called swan-necked flasks, okay? Because what happens is when you boil something off, when it cools down, it takes in some air, but everything is trapped right here, okay? So if you boil them and you wait, no growth. Boil this culture, break the stem off, what do you get? Growth. If you took those swan neck flask, you could actually see that there are some microbes in here, but it never makes it back to the solution, okay? So you could break that off and culture it and find out you got microbes there. Bless you. Okay, so this is the experiment right here, Pasteur, that disproves spontaneous generation. He invented pasteurization. What is pasteurization?
It's like a high heat for a short time.
Okay, there's a lot of talk lately about pasteurized versus non-pasteurized or raw milk. Okay, we pasteurize milk to do what? Kill microbes. Okay, and right now that includes viruses. Where does H5N1, the bird flu, like to hang out? What part of the cow? The udders of the cow. That's where it likes to hang out. Okay, we knew this a couple years ago when we first started seeing H5N1, that cow udders had a really high titer of this virus. Okay, so when you I'm going to ask you that question. So what happens is you get the milk. Have you ever been to a dairy? Anybody actually milk the cow? Yeah, okay. Let me ask you something. Is it nice and clean? No, okay? If you know the anatomy of the cow, where's the anus compared to the udders? Close by. Okay, think about this in terms of agriculture in California. 2/3 of California's water is used by agriculture, and it's not just to water crops. It's to what? It's to clean animals, to wash them off. Are they gonna soap and water each cow after they milk it? No. If you've ever been to a commercial farm, yeah, they don't do any of that, okay? And the cows sit in the grass, the cows do all sorts of things we won't talk about, okay? But, so is there gonna be bacteria in that milk? Yes. So what do? Okay, even with those nice electronic milkers that they have, they don't clean them between every animal. They don't. Why? Keep costs down. Water's expensive. Soap's expensive. So what they do is they just, rinse everything down. And so what are we seeing? We're seeing a lot of microbes in that milk. So what do? They pasteurize it. They raise the temperature of it enough to kill a lot of microbes and viruses. Now the cool thing about a virus, if you heat it up and you get rid of its protein code, its capsid, and heat it up enough that it breaks up the RNA, then it's not infectious anymore. Okay, where are we seeing H5? First of all, which state has the most H5N1 cases right now? Human cases. California. We have so many dairies that are in quarantine right now. Because why? It's spreading like crazy. I haven't heard about it. Well, we have a new president. Doesn't seem to like science too much. Okay? All right? You may like him. I liked him for Operation Warp Speed. I gotta tell you, he was right on top. Do you know about Operation Warp Speed? That was President Trump's, at the time, push to get COVID vaccines out. And he funneled all this money into the system, and my friends that actually worked on the vaccine were working 80 to 100-hour weeks. They were sleeping in the lab. I mean, we needed this out because, remember, December of 2020, we still didn't have a good vaccine that was out among the population. And so ERs, EDs were getting swamped, right? People were dying. So that's one of the things that I thought he was spot on. Part of my job was to meet with the White House on the White House call every Wednesday at 10 a.m. to hear what the new thing would be for the week and what to expect in different regions. And when he proposed Operation Warp Speed, I'm like, yeah, this is exactly what needs to happen. And he got the fastest vaccine out in history, something like that. Now, thank goodness we already had the RNA platform. It had been around for 40 years, but it hadn't been used. And this virus was a great one to use it on because it doesn't change conformational shape when it injects. They've been trying to use it for RSV. RSV changes when it enters the cell, so it was a little different. So that was one thing he did. Right now, not keeping track of H5N1, we got a problem. Why do we have such a problem? This keeps me up at night. Okay, why? We've got very, very high influenza that is easily transmitted. We've got an H5N1 similar virus. Will they come together?
Yeah.
Absolutely. As soon as H5N1 is transferred human to human, we've got a problem. Has it happened yet? No. Will it happen? Oh yeah. Oh yeah, it will happen. And if we're not surveilling, we're gonna miss it until it's too late. Now, right now, you can look up what the symptoms of H5N1, there's a lot of conjunctivitis and stuff like that. But, we really, really need to do virus surveillance, okay? Because then when the balloon goes up, we gotta have something here. So, this is what concerns me about raw milk. What happens with raw milk? Does it get pasteurized? So what does it have? Bacteria, protists, viruses, okay? Is there any nutritional difference? Absolutely not. You can check the literature. There is no nutritional difference between raw milk and pasteurized milk, okay? And all you're doing is exposing yourself to things that can potentially make you sick. I mean, look at the cats that are dying from the unpasteurized food. Oh, I want to give my cat fresh food. Well, cats seem to be particularly sensitive to H5N1, and there have been a lot of deaths. Why? Because their food isn't pasteurized. Their food isn't clean. And people are like, oh no, the cats. I'm like, how about the people? I mean, I know the cats. So anyway, talk about pasteurization. Let's talk about endospores and sterilization. What is an endospore? What is an endospore? You ever heard of an endospore before? Okay, what is it?
Something that's hard to kill.
Oh, it's very hard to kill, okay? Some bacteria form endospores. They're very environmentally resistant structures. So that allows a bacterium to survive hostile environments. And then when the environment changes and gets a little more friendly, then they'll come back. Okay, can you kill all endospores with bleach? No, you have to use a strong hydrogen peroxide, okay? And so when you look at what Cohn did and what Tyndall did, okay, and this shows some of the different endospores, and some bacteria exist in two forms. Wow, that is just jumping all the time. Okay, so heat stable form, which is an endospore, a heat sensitive form that if you heat it up, will kill you. Now let me ask you, are these endospores metabolically active? No, they kind of shut down. It's like a hibernation, right? It just kind of shuts down. So can you give an antibiotic to kill an endospore? No, if it's not doing metabolism, it won't work, okay? All right, so then there are some bacteria that you see, you got heat treatments, and they call it Tyndallization, where you heat things up under high heat and pressure to kill it, okay? And here we are in the 1870s. That's not that long ago, okay? Just seems like it, but it really isn't that long ago, okay? Any questions about endospores? Okay, as you do your disease cards, you're going to find bacteria that make endospores, okay? That's important. I'll give you an example of one that does. Anthrax, okay? All right, Bacillus anthracis, it forms endospores, okay? Now, we know about weaponized anthrax that, they make into a powder and you inhale and it affects your lungs. But there may be a time, depending on where you're practicing, that you will find cutaneous anthrax that comes from spores, okay? And it's in, like, when you're tanning something, like tanning a hide, sometimes you get spores. Sheep shearers, those that, buzz the sheep, the anthrax spores come from the soil. And so sometimes you'll see people that work on farms that shear sheep, they'll get a cutaneous anthrax sore on them, okay? And you treat it. Will it go to their lungs? No, it's different. It's cutaneous. It's on the skin, okay? Well, could it still kill them? Potentially, but not like the respiratory anthrax, okay? So, okay. All right, let's talk about the germ theory of disease. That, hey, germs cause disease. That didn't come around until the 1800s. And Semmelweis noticed that the death rates were higher in maternity wards that were staffed by medical students than those that were staffed by midwives. Okay, those of us that work in medicine, what month is July known for? What is July? You never want surgery in July. You never want a procedure in July. Why is that? All the new residents come. Residents match, that's when their residency starts, is July. So yeah, get it done in June. You think I'm joking? I'm not. Get the experience. Yeah, that's like one of my worst nightmares, is like having something significant happen in July with all the new residents. So why? Well, because they've been to medical school, they're medical doctors, but there's nothing like experience, right? There's nothing like the experience. So so you get these medical students, and what do you think the medical students were not doing, that the midwives kind of had learned? Wash your hands. Yeah, wash your hands. And it shows you, where you miss, and where do you miss? Usually your thumbs, right? Okay. So the death rates decreased in the summer. Why? Because probably washed their hands more, actually. I don't know what their rotation schedule was, but maybe by then they had enough experience. Okay? All right, so remember Semmelweis, okay? So if I were you, if I had a little notebook or something by me, I'd be writing all the scientists down. So when you go and study, you've got kind of a master list, and then you can say, okay, this is what they did. All right, cool. All right, Lister, Joseph Lister, the father of modern antisepsis. That's why we've named it Listerine, right? It was after Joseph Lister. Okay, so you're in the 1800s, no one's washing their hands. He read Pasteur's paper on the microbiota. He read Pasteur's. You okay back there?
Yeah.
Okay. Read Pasteur's papers. That's what scientists do. We're always reading. What is everybody else doing? And they were looking at what were the microorganisms that we're seeing causing gangrene. How many have seen gangrene? You seen it? Describe it.
It's like,
It's gross.
yeah. It's like when, how do I explain it? It starts to be like weird color, like dark green or like.
Green and purple and black. And what happens to the tissue itself?
It dies.
It dies and you get gas, you know, that's produced, and so you get disfigurement of the infected area. It's a nasty, nasty infection, anaerobic, so it doesn't like there. So yeah, gangrene is really nasty. So what did he start doing? He thought, ha! Well, if Pasteur is doing something, let me try something in surgery. And so he used antiseptic, carbolic acid, and he sprayed all of the patients, all of the, the surgical instruments, the wounds, the dressing, and guess what? His incidence of gangrene went down significantly. Okay? Just by this little antiseptic, carbolic acid. Okay? That is so amazing. Okay? All right. Robert Koch, culture techniques in the 1800s. Okay? He used this compound called agar, which is a carbohydrate that you get from seaweed, and then added nutrients like carbohydrates and proteins. It didn't melt, the bacteria couldn't digest it, but it made a nice like matrix for the nutrients to be in there. And he invented a technique for isolating pure bacterial colonies using a special dish, which you know as a petri dish, right? And he was able to show that a bacterium caused anthrax, and came up with a list of rules called Koch's what? Postulates, right? Koch's postulates. Now you haven't streaked yet, have you?
No.
I'm not personally like taking off, I don't want to know that, but in lab you haven't done streak plates? I think that's this week, isn't it? Yeah, this is really cool. So when you get a sample, let's say you're swabbing for a sinus infection, okay, swab. You're gonna put it on the plate and you're gonna see what grows, but oftentimes the microbes are really dense and you have a mixture of microbes there. What you are looking for is colonies, because when you grow a colony, what do you know about it? One colony came from one cell. So you know everything that's in that colony is the same, okay? It did mitosis or binary fission, and it did what it needed to do and made a colony, okay? We can't, if we were to sample from here, we can't tell anything. If we were to sample from up there, we can't tell anything. But you can see where we start to get individual colonies, then we can do some experimentation, okay? So let's look at that. There's some aseptic technique. All right, so you take a sample from a patient, put it in the petri dish. Notice how they move the lid. You're going to learn how to do that so you don't get environmental contamination. Okay, streak, and then you can apply it. Once you find out what is here, then you can hopefully treat the infection. However, there's a lot of infections we're running out of treatments for, right? So, okay, before we go on to the next slide, I want you to take a minute with your study buddy, okay? Study buddy, you're sitting by your study buddy, okay? Take a moment and write what you know. I'll give you 1 minute. Write what you know about Koch's postulates, okay? I'm just on a piece of paper. Who needs a study buddy? Okay. Do you need a study buddy? Yeah, okay. You want to come over here, right here? Raise your hand if you need a study buddy so people can find you.
Is it fine if I just group with them? So,
Yeah. Well, she's right here. Yeah. Who needs a study buddy? Find them. Okay, give you a minute to find a study buddy. Raise your hand if you need one. Okay, who still needs one? There's one here. Do you still need one? No? Okay.
hi.
Do you still need one? Okay, there you go. Come on over. Just for a little bit.
Honestly.
Okay, on a piece of paper, blank piece of paper, 1 minute, 1 minute to write everything you know about Koch's postulates. Okay? Ready, set, go.
I have nothing. Girl, you literally have a whole thing.
Oh, I did.
What are
I
you
was like,
talking
what?
about?
I didn't read it. I was like, okay. So we can write it on a piece of paper.
Yeah, I picked up a piece of paper.
So we associate, isolate, incubate, and then
Inoculate, you mean?
inoculate, and then re-isolate.
Yeah, so I don't have anything. I'm sorry.
Oh, which lab are you in?
Okay, show me Koch's postulates.
No, we're in the same lab.
Oh, I think you said like,
Yeah, we're on the same table we've been.
uh-huh.
Like we're on the same side.
Yeah. Probably then. I'll just copy that one.
Yeah, that's good.
Okay, time's up. What did you get? Such a happy song. Okay, there we go. Okay, so Koch's postulates. All right, this was technically last week's stuff, okay? And I'm just talking about how to be a better student, okay? How to do this. All right? It's not enough just to read through the PowerPoints. It's not enough. You've got to be interactive, writing down what this is. Okay? Tell me about Koch's postulates. What's the first step?
Associate,
What's the first step?
associate.
Okay? All right, let's do this here. Okay? Do you think this is important? Yes. Okay? And it's not just, hey, I remember these steps and blah, 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 blah. Okay? Let's go through these one by one. Stay here. Stay with your folks.
Oh.
Okay? Okay. Koch's postulates. We're going to see this all the time. Why? Because this is how you prove the causative agent of disease. It's Koch's postulates. Okay? I'm going to start up here with this dead mouse. Is everybody with me? You're looking at the screen? Okay. All right, dead mouse. So what am I going to do? I'm going to culture from the infections of that dead mouse, get a colony, okay? And hopefully I can get enough that I can actually see the microbe. If I do streak plating right, I can do that. Then what do? I take that microbe and I inject it in a healthy animal. Okay? Whoops. Now, if that animal survives, is this the infection that killed this mouse? No. If this animal dies, probably, that's a good possibility. Is it 100% yet? No. No, it's not 100% yet. What do we have to do? We have to culture that mouse to get the pathogen and see if it's the same one that we isolated up here. And in this example, it is. So whatever we cultured here caused the death of this mouse. Okay? That's Koch's postulate. And yeah, there are 4 steps: associate, isolate, re-isolate, and inoculate. Okay? For me, having trouble with words sometimes, I'd rather look at the picture and go through it. Okay? So we associated, hey, this mouse died of disease. We isolated it, we re-isolated and inoculated. So we make sure that whatever we test, we're pretty sure that's going to cause it. Okay, all right. I don't want to, wow, we're a little running time. This is something that you can do. What we did is just called a 1-page test. Did we talk about that before? Okay, whenever you want to see how well you know something, take a blank sheet and a timer. You can do this anywhere, except driving down the freeway, not recommended. Okay, so get your thing out, start writing. Okay, I'm going to remember all of the important scientists. Write them out. Not just like, oh, it was this person. Write them out. Remember, we're trying to get connections. Okay, give yourself a minute. If you can't do anything and you can't write anything, you don't know it. Okay, you don't know it. You got to do the 1-page test for anything. It really does work. Just find out where the holes are. Okay, you can do it with your study buddy too. Okay, let's talk about the golden age of microbiology here. Okay, Pasteur and Koch were enemies. They were rivals. Okay, competing constantly, and sometimes when people compete, they actually move further than if they didn't. Okay, but we're going to look at next the beginnings of immunology. And who belongs in this? Edward Jenner, right. Okay. Edward Jenner was a physician, and he had a patient that was a young milkmaid, and said, well, I'm not getting smallpox because I have cowpox. Looks like the same. She's a milkmaid. She's milking those cows. Those cows have diseases, and it presented with cowpox. And so what did Jenner do? Okay, cowpox is very, very mild compared to smallpox. And so Jenner had this great idea. He said, well, how about if I take some of the swabbings from this milkmaid's sores and inoculate others with it? Well, guess what happened? He had the first acquired immunity from an immunization. And he called it a vaccination. Because why? What is vaca in Spanish? Cow. Yeah, that's where it comes from. Isn't that neat? Yeah. So, thank goodness. First of all, that milkmaid for saying, hey, making that observation. And good for him as a physician saying, wait a minute, would this work to prevent smallpox in the community? And the answer is yes. So from 2017, these are the deaths caused by vaccine preventable infections. Crazy. Measles is much higher now, but yeah. Okay, let's talk about Paul Ehrlich, okay? Were people having sex in the 1900s, early 1900s? Yes, all the time. We found that throughout human history. It's probably why we're here, okay? Now, did they have STIs in the 1900s? They've had STIs forever, okay? Yes. And one of the STIs is one of my favorite ones, syphilis. I love syphilis. You know why? It is caused by a spirochete. Okay, syphilis can be really hard to diagnose if you don't catch it early. Because, okay, you get it in your nether regions, right? And it's like, oh, it burns, it itches, I got sores. You don't say, oh, I'm going to let it go. Well, guess what? With syphilis, your immune system will get it for a little bit, will cover it. And you'll think, oh, I'm all better. See, I didn't need to go get swabbed. But what is happening is that spirochete is burrowing into tissue. And it's going to go elsewhere because of its shape. Where does it go? Anywhere it wants to. The brain, the eyes, the ears, the hands. And so when you have syphilis, you can have primary syphilis, which is your initial infection. You can have secondary syphilis, where it's gone somewhere else, and tertiary syphilis, right? And we know famous musicians that got tertiary syphilis, right? Beethoven went deaf from tertiary syphilis. He was a lover, not a fighter, and so he got syphilis. Okay? So, yeah. So, we didn't have antibiotics. But Ehrlich came up with an arsenic-based drug to treat syphilis. Is arsenic toxic? Absolutely. When you got treated with syphilis, it wasn't like, I'm going to pop a pill. You were sick for a long time trying to overcome the infection. Okay? In 1922, along came Alexander Fleming, who we'll talk about in a minute, that discovered there was an enzyme, lysozyme, in tears and saliva and sweat. And this was the first body secretion that had chemotherapeutic properties. Okay? And then in the 1930s, we had sulfonamides that are synthesized and still used. Okay? All right, here's Alexander Fleming in 1928. Alexander Fleming was a slob in his lab. Thank God he was, because he had petri dishes. Like, look at this. I'm like, no, don't do this. He let some petri dishes open, and he shouldn't have let open. And what ended up growing was a fungus in his bacterial colonies. Now, I would have been really pissed off. I've had contamination in animal tissue culture and human tissue culture and bacterial tissue culture. But let me show you what happened. Here's this penicillin colony. Does anybody know what this area is where nothing is growing? That's Bio 1. This is the zone of inhibition. Okay? And you saw this in Bio 1, or you should have seen it in Bio 1, where you get a zone of inhibition. So the bacteria, you could see the bacteria should be growing there. What is the penicillin doing to the bacteria? Killing it off. It makes a clear area called the zone of inhibition. And when that happens, what does it mean? This colony of fungus, a penicillin, is secreting chemicals into that area that was killing off the bacteria. Okay? So, wow, thank goodness it was a little messy, because we were able to get penicillins in the 1940s. And that changed the course of World War II, because now if we had injured soldiers, we could give them penicillin. So, yeah, kind of cool. All right. So these are some of the other great areas of topics in microbiology. Okay. Now let's talk about microbes in general, bacteria. Bacteria is found in the fossil record, and it's backdated to 3.7 billion years ago. Okay. So the bacteria have been around a lot longer than any of us. And it makes sense, because they're very agile, they can do amazing things, their biochemistry can change in order to survive. We're not that flexible. I mean, when you look over here, this is where humans appeared. Wow, okay? They've been around a long time to get their specialties on, okay? So we've got two types of cells. You remember this from Bio 1, prokaryotic and eukaryotic. And then we have viruses, okay? And let's see, what kind of cell is this one? Prokaryotic, and here we have a eukaryotic cell. Here's our friend Giardia that we talked about earlier that contaminates water. It's a protozoan, it's a eukaryotic cell. This is a bacteria. What are these things on the end of the bacteria here? Flagella, yes, okay. All right, what is this creature here? It's a virus. This one happens to have a lipid envelope in that. Are viruses living or not? No, they need a host. They're kind of parasites. Okay, we're going to go through this pretty quickly because, again, this is review. If you're not clear with it, get your Bio 1 book back out, go online, try and find out. But we've got 3 domains, bacteria, archaea, and eukarya. We're not going to talk about the domain archaea, even though they're prokaryotic. They're extremophiles. They don't cause disease. you're not going to see them in the clinic. So we're going to focus on kingdom bacteria. Okay, so we go through the classification system, okay, with our 3 domains, all right? This just shows you the classification that you have for humans, dogs and wolves, and bacteria. So you can see we worry about the genus and the species. The genus is always capitalized, the species is not. On your quiz on Wednesday, you need to write them correctly, or else it's wrong, okay? Make sure that you know how to write genus and species, and you spell it right, okay? All right, here's our taxonomy. Dumb kings play chess on funny green squares. Domain, kingdom, phylum, class, order, family, genus, species. Okay, so you can read through this, a little bit of archaea there. Here's a nice table that you can use for reference. You have pronunciation, and you can Google the pronunciation on these so you can practice them. And if you notice, this is a genus name. How come? It's capitalized. Good, good. Okay, the Burgess Manual, that's it. Burgess Manual of Bacteriology, that is kind of like the standard. Okay. Ooh, look, a spirochete. Ooh. Syphilis. All right. Dichotomous keys. Okay. How many of you used the dichotomous key? This is an Bio 1 thing. Okay. If you haven't used the dichotomous key, pay attention to this slide. Okay? Dichotomous keys are what microbiologists and biologists use to categorize things based on characteristics. If I took out a coin, I would be able to find, I don't have a coin. Who has coins anymore? But yeah. Okay, so let's say I've got a nickel. Okay, remember what a nickel looks like? Is it smooth edged or round edged? Smooth. So then we go to 2. Is it silver or copper? Silver. Okay, it's a nickel. All right, kind of fun, huh? We do the same thing with microbes. Okay, so there's the dichotomous key, so you can tell what the different microbes are. I don't expect you to do this yet. You haven't learned a lot of shapes, but I'm just telling you this is the direction we're going, okay? All right, viruses and prions. We've talked about viruses. They have genetic material surrounded by a capsid, a protein coat. Prions are what? What are prions? Protein, proteinaceous infectious agents. Yeah, proteins that change other protein shape. Okay, now remember, most microbes are harmless. 95% of them are our friends. Aw, they're so cute. Do you have these microbes? I got a bunch in my office. I should bring them in.
Isn't that one a virus?
This one is a virus. This is a T4, yeah. This is E. coli. This is Giardia. Yeah, I don't remember the names of all of these. Yeah, that's a bad mother. Okay, this looks like a fungus. Yeah. So anyway, all right. So we're up to date with chapter 1. We go until when? 11. We got 10 minutes. Good. Let's do some epidemiology then. Did you learn something in chapter 1?
Yes.
I hope so. Yeah, something new. That's always good. Okay. Okay. More people were killed. The 1918 influenza killed more Americans than died during World War I. Yeah, who's going to win? The microbes will always win. Okay? So, we've got a number of key terms here. Okay? What is a pathogen? Any disease-causing agent. Good. What is contamination? Pathogenic microbes on the on the skin or the surface of a host. Infection is invasion of the host by a pathogen. Right. Etiology. This is the causative agent of disease. And when you have an ideological agent, that is a scientific name of the casual agent. Okay? So, for example, we talked about the casual agent anthrax. The causative agent is Bacillus anthracis. Okay? Do you need to know both? Yeah. Yeah. Okay. All right. Lots of definitions. I think I will probably stop there. You've turned in all those good things. And tell me what's going to happen Wednesday morning at 9:35. We're going to have a Quizzy Wizzy. We start at 9:35. Okay. All right. First Quizzy Wizzy, it's going to be chapter 1, the syllabus, and the disease cards. Okay? Yes?
Are we gonna need the scan code for the?
No, I'm going to give you an answer sheet. Okay? All right. I'm glad you asked that. Very good. Okay. I'll see you Wednesday.